Now let's spend a few minutes here exploring the Lorentz transformation. To start, let's remind ourselves where we were and what we ended up with. The goal was, if we have, again, Alice, in this case, being stationary, her frame of reference, Bob going by at some velocity v. Of course, Bob in his frame of reference, he's stationary. He sees Alice moving the other direction with velocity v. And our goal was to have a simple set of formulas such that given coordinates of an event in Bob's frame of reference, xb, yb, zb, and tb, we could easily transform those into the equivalent coordinates for that given event in Alice's frame of reference. And obviously we're not going to redo the derivation here, but to remind you where it came from, we had an argument such that the form of the equations had to be linear. And what that meant was that we couldn't have any, given xb, yb, zb, and tb, we couldn't have any xb squares or t squareds or square roots or things like that. The reason being, the argument we put forward is that if you have, let's consider time, okay, so say ticks of Bob's clock, they're equally spaced, 1 second, 2 seconds, 3 seconds, 4 seconds. Now when you transform time into Alice's frame of reference, as we know, there's this time dilation effect. So potentially the distances between ticks can change, but we should have uniformity there. In other words, if Bob's ticks, just as an example, are 1 apart, 1 second, or whatever unit of time we're using, 1, 1, 1, 1, then Alice could be between her ticks 1.5, 1.5, 1.5, but we can't have something like where Bob is 1, 1, 1, 1, Alice is 1.5, 1.8 between the next tick, 2.3 between that tick, and so on and so forth. So the distance between ticks when you do the transformation has to be the same. And you can make a similar argument for the measuring system for lengths, that you can have differences between Bob's length scale and Alice's in terms of a length contraction effect, as we've seen, but you can't have non-uniformity where Bob's measuring system is uniform and then it transforms into a non-uniform system in Alice's, because you get inconsistent results that way. So that was sort of a hand-waving argument, not a rigorous argument, but the idea was that then we had to have something like this form where G, H, M, and N were unknowns. We would like to find out what those were. And so we took these equations and plugged them into our invariant interval equation, which we had previously derived for the situation where you have essentially 2 frames of reference, or really multiple frames of reference. The invariant interval is invariant, is constant for all frames of reference. So we knew that was true. Plugged these in here, did a lot of algebra, and got these results here. That TA, given xb and tb, TA was gamma v over c squared xb plus gamma tb, where gamma, of course, is our Lorentz factor, and x sub a, gamma times x sub b plus gamma v t sub b. We rewrote those. We just moved things around a little bit and put them in this form. For TA and xa, it's a little bit easier to memorize them. In that form, TA equals gamma tb plus v over c squared xb. xa equals gamma xb. So notice this sort of parallelism here between TA, tb, xa, xb. Slight difference in the second term in each. I've got vtb over here in the xa and v over c squared xb. Part of the reason for that is the units have to work out. Here we've got to have units of length, and a velocity times the time gives us units of length. Here we have to have units of time throughout the whole thing. So a velocity divided by another velocity squared times a length, if you work that out, will give us units of time. One thing we didn't mention last time we were doing the derivation, we were concentrating really on xb and xa, ta, and tb, was what happened to ya, yb, za, and zb. Well, remember last week when we did the analysis and showed that you don't have any width contraction effects or height contraction effects, and therefore in the perpendicular dimensions, if our direction of motion is in the x direction, then the y and z directions, there are no length contraction effects, width contraction, height contraction, radial contraction effects, and so those equations are very simple if we were doing something in 3 dimensions. And of course, normally we're just working in 1 dimension for simplicity. So Those are our Lorentz transformation equations. What we want to do now is rewrite them slightly and then investigate them a little bit to see what the math is telling us here. It's also a good idea to not just say, okay, there are the equations, let's go use them, but to understand them better, find out what they're telling us, whether they're consistent, maybe we made a mistake someplace, and so on and so forth. So to do that, let's rewrite them up here in slightly different form, because these are A's and B's, and sometimes it's easy to forget who's moving here, who's stationary, and so on and so forth. So in our derivation, we assumed this was from the perspective of Alice being stationary, Bob moving with velocity v. We'd like to have similar set of equations for what about Bob's perspective? If he considers himself stationary, then Alice is moving in the other direction with velocity v, negative v in essence, in the negative direction. And therefore, what would the equations look like in that case? So let's, first of all, rewrite these. And so instead of A for Alice, we're going to have rest for the frame of reference that's considered to be at rest. So we'll have something like this. We'll say T, let's get a better pen here, T rest equals gamma still being the Lorentz factor. TB is our moving frame, so we'll just say T moving plus V over C squared X moving. Okay, so those that in this case would refer to Bob, and then X rest equals gamma X in the moving frame with respect to Alice. Okay, Alice is being assumed at rest here, plus V T moving, not rest. Okay, so there's, we got that. Now, I should say another way we could have labeled these, and you want to choose a way that makes sense to you. Often we'll say we've got the rocket frame and the lab frame. And in many textbooks you'll see it that way as well. So if you prefer that, you could certainly use it. So instead of the rest frame, that would be the lab frame, and then the moving frame is the rocket frame. And sometimes that's even a little easier because then you can visualize, you can picture, okay, I've got the rocket, and I've got the lab, the observer, Alice in this case, in the lab. So you can either use lab and rocket or rest and moving there. Well, what we want to do in part one of exploring this is focus on this equation here and just see what happens when we put in some different values here, see if the results make sense based on our previous understanding of what we've been doing with things like length contraction and so on and so forth. So to start off, what happens if, let's just say, let v equals 0. What if the velocity is 0 here? Well, we know if the velocity is 0, then gamma, just remind ourselves of gamma, 1 over the square root of 1 minus v squared over c squared. So if velocity is 0, gamma is 1. So we know gamma equals 1 in that case. So what does this equation become? Well, we get x rest, Alice's perspective, gamma is 1 here, equals x moving, and v is 0, so this is 0 as well. So we just get x rest equals x moving. In other words, if we were thinking about the, again, lattice of clocks here is the underlying foundation of our observations. Alice has her lattice of clocks, and that's her measuring system for length and time. Bob would have his as well. If v is 0, they're not moving with respect to each other. So any measurement that Bob makes here, out here Bob says, okay, in his moving frame, I see something at xb, or in this case we're calling x moving, the moving frame, at 23.8. Well, since they're stationary with respect to the other, Alice would also see that on her system as 23.8. So that's what this is telling us, and we hope we get this answer, otherwise something went wrong along the way. So that's one simple check we can do. What happens if, let's just get some room here. So that was our first test case. That made sense. Now let's say, let's let let's not let v be equal to 0, but let's make it really small compared to the speed of light, sort of everyday type of velocity. So if v is much less than c, then gamma is approximately equal to 1. Right? If v is much less than c here, this is essentially 1 minus pretty close to 0. 1 divided by the square root of pretty close to 1 is going to equal 1. So gamma is approximately equal to 1. And so what do we get then? So we get x rest equals gamma, we'll say, is approximately equal to 1 here. And so it becomes x moving in the moving frame. And by the way, just again, the terminology here, this does not mean x is moving. This belongs an x coordinate, an x measurement in the moving frame. Okay, so just fix that in your mind. Don't get confused about that. So x rest equals x moving here plus a velocity. Okay, it's going to be non-zero. It's going to be much less than c, but still non-zero, times t in the moving frame. In other words, on one of Bob's clocks in the moving frame. Well, what does this remind ourselves of? Hopefully, it reminds ourselves of the Galilean transformation, especially because if we go back up here for a minute and look at the t equation, if v is much less than c and gamma equals 1, look what we have here. Gamma, of course, being 1. If v is much less than c, this is a very small number, v divided by c squared. Not just v divided by c, but v divided by c squared. That's a very, very small number. And essentially, we just have time in the rest frame equals time in the moving frame. And therefore, this is just t. And so that would make this a Galilean transformation, where t is the same for all observers, all frames of reference, and you just have your basic x in the rest frame equals the x value in the moving frame plus v times t. Essentially, this shows how far Bob has moved along. And so if he measures something, again, say at 23 out here on his lattice of clocks, his measuring system, but he's also moved a certain amount, then the distance to Alice, the x in the rest frame, is the amount Bob has moved plus the amount he measures out to 0.23 on his measuring system. And so basic Galilean transformation there. So that checks as well, because we know that works in our everyday experience when velocities are much less than the speed of light. Okay, so now though, what happens when we have velocity being large? Let v be large. Obviously not equal to c, but up there someplace. So let v be large. Then what do we have? Well, essentially we just have this equation. We can't do any simplifications of it. But let's split it apart here and take a look at it. So we've got x in the rest frame. X in the rest frame equals gamma times x in the moving frame plus gamma times v times time as measured in the moving frame, in Bob's frame there. All I did was multiply that by gamma and then that term by gamma to split it apart here. So essentially this is very similar to the Galilean transformation which we were just talking about. In other words, for Alice here, Bob is going to measure some event at some x value in his frame. Maybe it's at 23 again on his lattice of clocks and his measuring system out there. So where is that going to occur on Alice's lattice of clocks? Well, it's going to occur, again, the general idea is how far has Bob moved, what time is the measurement being made, and then plus whatever he's measuring out here. We're assuming it's a positive value. So we're assuming he measures it at 23 out here, but in the meantime, he's also moved over here, and so the distance for Alice will be that distance plus that distance. So this looks similar to the Galilean transformation, same concept, except we've got these gamma factors in here. And in fact, if Bob is measuring this at his time t equals 0, and we also assume that they're right together at t equals 0, Bob is just passing by Alice at t equals 0. So if we're measuring this at t equals 0 for Bob, t moving equals 0, then this term goes to 0, and look what we're left with here. That's our length contraction equation. In other words, what that is saying is if Bob says, okay, right at t equals 0 on my clock, I measure out, I see something at 23 out here. Alice, remember, length in the moving frame is going to be contracted. So Alice here will see x moving as less than her value for whatever the distance is, 23 or whatever. Okay? So another way of saying this, the way we wrote the equation before, was x in a moving frame equals 1 over gamma x in the rest frame, the stationary frame. Just to emphasize, because gamma is always greater than 1, greater than or equal to 1, of course, that means the moving value as measured by Alice in this case is less than, you take x rest, multiply by maybe gamma is 2, 1/2, and that you get a smaller value. So this is the length contraction effect, and essentially that's built into the Lorentz transformation, as it better be. If it isn't, then we've got something really wrong here. Either our original conclusion with length contraction was incorrect, or our Lorentz transformation derivation was incorrect. So what we see here is that, first of all, we can get the Galilean transformation out of this, that equation, for sort of everyday velocities, much less than the speed of light. We also see that when v is large, that we get the length contraction effect coming out of it, where again, length contraction in the simplest case is simply when Bob measures something at t equals 0, so he's there, Alice is there, Bob measures a certain length, and then Alice gets that length as well, and you get the length contraction effect going on there. So that's in there as well, and so that's exploring the x equation here. In our next video clip, part 2, we want to do a little bit of exploration of the time equation.